Swayam Prabha. Digital India. Educated India.
Welcome to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We are from Civil Engineering Department, IIT Kharagpur. This course is divided into two parts. Environmental Chemistry is the first part that I will cover, and the next part is the environmental microbiology that will be taught by Professor Sudha Goel. Now, this is my module 6 and 27th lecture. In my earlier modules from 1 to 5, I have explained acids, bases and salts in my first module. In my second module, I discussed about the chemical equilibrium. In the third module, I discussed about the chemical kinetics, and fourth module I covered the catalysis. Fifth module I told about the chlorine chemistry and nitrogen chemistry, and in this module I will cover radioactivity. In the 26th lecture I covered radioactivity part A, now it is part B. As I told you that this topic is very interesting topic, and in this lecture I will tell you something regarding the theory of radioactive disintegration, and then half life and average life, radioactive equilibrium and unit of radioactivity. Now, radioactive decay, the two scientists Rutherford and Soddy, you all have heard the name Rutherford, very famous person. In 1902, they have investigated the radioactive elements uranium, thorium and radium, and the behavior was explained. So, that time during this time it has just discovered, radioactivity property was just discovered by Becquerel and Madame Curie and Pierre Curie, and many scientists started their work on this particular topic, and then as you have seen here, Rutherford also doing some experiments, and they have explained the theory of radioactive disintegration. Now, what is this theory? What does it say? The theory says that radioactive elements undergo spontaneous transformation, that you have already seen, from one atom into the other, and radiations are emitted during the process. So, basically one atom is transformed into another atom. Okay. This was new that time, the concept is totally new, because previously we knew that an atom cannot be changed to another atom. But when radioactivity was discovered, then first time it is realized that one atom can go to another atom. Okay. And radioactivity means it is transformed spontaneously. Okay. And during that transformation, what is happening? Some particles are coming out, so some radiations are coming out, and in a alpha decay, the product element, by now you know what is the alpha particles. Okay. So, when some element, some nucleus is giving out some alpha particle, then alpha particles has mass, 4 mass and 2 charge, that we know. So, what will happen when some nucleus will give give out some alpha particle, then what will happen? That then what will happen? We will see that the new element that is formed, the product element, it is called product element or daughter element, parent element and then daughter element, or parent element and product element. So, product element will have 4 mass unit less and 2 charge unit less. 2 charge unit less means atomic number 2 unit less. Okay. But what is periodic table? Periodic table, how it is arranged? We know that periodic table is arranged according to the atomic number, not the atomic mass. So, when 2 atomic number, 2 unit of atomic number will be reduced, then it will go where? What will be its new position in the periodic table? The new position, as a result, the product element get displaced 2 positions to the left in the periodic table. This is the very important. Okay. So, alpha particles are nothing but helium nucleus, that means it has 4 mass unit and 2 charge unit. So, when one parent element give out 1 alpha particle, then the product element will get displaced 2 positions to the left in the periodic table. Okay. Because periodic table is arranged according to the atomic number, according to the increase of the atomic number. So, 2 units less means 2 positions it will shift to the left. The example is given here, radium. Radium, I already told that what is the meaning of this. Radium 226, it is the atomic mass and this is the atomic number. So, radium when gives out 1 alpha particle emission, upon alpha particle emission, so this will be reduced by 4 units. So, it will become 222 and then this one by 2 unit. So, it will be 86. So, the position of radon will be 2 units left towards in the periodic table compared to radium. In a beta decay, when some element, some nucleus will radiate the beta particle, then what will be the position of the daughter element? Here you see, here it is written product element, here it is written daughter element. Okay. So, what is the position? Beta decay, in a beta decay the daughter element has the same mass, because it is electron has no mass, same mass of the starting element, but the charge is increased by 1 unit. 1 negative charge is less means 1 positive charge is more, right. So, because beta particles are electrons, as a result product element is shifted to the next position, okay, to the right in the periodic table. So, 1 negative unit is less means 1 positive unit is more. So, what we see here, lead is the parent element. So, it has the atomic mass 210 and atomic number 82. So, 1 beta particle is emitted, okay, then this will become plus 1. So, 83 and this will remain the same, okay, because electron has no mass. So, mass will be same, but this atomic number will be increased by 1. So, what will be the position then of the daughter element? It will be 1 unit shift in the right of the periodic, in the right side of the periodic table. Okay. Now, law of radioactive decay. The amount of radio element that disappears in unit time is proportional to the amount present. So, you see the similarity in the as the first order reaction. Okay. The rate of decay, rate of disappearance, here radionuclei. So, the rate of disappearance of the radio element is a rate of disappearance of radio element rate means per unit time of course, okay, is proportional to the amount present. Okay. Just like the first order, rate is proportional to the concentration at that time, that was the first order reaction, right. Here also you can see dN dt is minus, why, because this is disappearing. So, minus dN dt equals to lambda into n. So, what is the difference you see here? In this case for radioactivity we write n usually. If you write C, that is also okay, but we usually, this is the means convention that we write n, capital N, and in there in chemical reaction we write the rate constant or specific rate constant, we write usually by small k. I told you that it is small k, but here we write lambda. This is also specific rate constant, but here we tell that decay constant, because it is the radioactivity. So, element is decaying, the starting element is decaying, the parent element is decaying, that is why it is called it is not called rate constant, but it is called decay constant. So, other things are same. N, what is N? This is the number of atoms present at that time, and N0 is the number of atoms present at 0 time, starting time. Okay. So, if you integrate same way as we have done for, if you remember, for the first order reactions, then upon integration we will get ln n by n0 is equals to minus lambda t, or in other way you can write ln n0 by n is lambda t. Okay. And then n is equals to n0 into e to the power minus lambda. So, it is like this, that is the exponential curve. Okay. So, here you can see that this is the time and this is the relative activity percent, or if you start with say 100 is a concentration, then with time it is like exponentially it is decaying. And then half life, here also in case of first order reaction you have seen that concentration to come down to its half concentration, you starting concentration to half of the starting concentration, the time that is taken is called T half, but there you have written small t half, but here usually we write capital T, capital T. So, here you start with 100% activity 100 and then you come to 50. Okay. So, the time that is taken here, it is the half life of that particular radio element. Then again when you start with 50 and then you come to 25, you see here another T half is taken. So, if it is 4 hours, then again 4 hours. Then again if you start with here midpoint of this is this one 12.5, then you start from here, then you see another T half is taken, this way it will go. Okay. Now, if you look into the equation, then you will see that at that case when it is half life, then you see that n by n is equals to n0 by 2, okay, because the concentration is half. So, n is equals to n0 by 2, and then we can write from equation 3, you can write ln 2, n0 by n means ln 2, okay, lambda into T half, in that case it is T half. So, this is the relation for this type of radioactive decay, this is the relation, it is similar as the first order reaction, T half is equals to 0.693 by lambda, or lambda is nothing but 0.693 by T half. So, what we see here, it is independent of initial concentration. Okay. How much amount you start with, it does not depend. Okay. Half life is always same and it is characteristic of a particular element. Okay. Lambda is also characteristic of a particular element. This is characteristic for an element. Okay. So, this is very important for the radioactivity. Radium, say for example, radioactive radium, it has particular half life. Uranium 235 has particular half life. Okay. Other radioactive element has some carbon, carbon also if it is 14 carbon then it has some particular half life. So, it is characterized by the half life, it is very important for radioactivity. Now, half life, the half life of a radioactive atom is unique property. Okay. It is independent of the initial concentration, just now we have seen, it is only dependent on the decay constant. Okay. If decay constant you have to find out, if you know the T half you can easily find out the decay constant. If you know the decay constant you can easily find out the T half. Okay. But average life is little different. Okay. It is not the same as half life. Average life of a radioactive species can be found out from the sum of the times of existence of all atoms divided by the initial number. Okay. So, all atoms if you how much time it is staying, if you sum it up, okay, and then divide by the number of atoms, then you will get the average life. And it is observed that it is average life, it is given by small t usually, then you will see that T is nothing but 1 by lambda, and T half is how much? T half is 0.693 by lambda. So, average life is greater than the half life by a factor of 1 by 0.693, that means 1.44. So, average life is higher than the T half. Okay. The decay process when applied to large number of atoms, then you will get appropriate values, accurate values. So, decay process when applied to a large number of atoms can help us to measure the number of disintegrations occurring in a given time intervals. Okay. Otherwise, if the number of atoms is small, then you will not get the accurate result. Okay. Now, let us do one problem here based on the half life, as you have already learnt what is half life. Okay. So, what is the problem? Strontium 90 strontium. Somewhere you will see that instead of writing in this fashion, it is written strontium hyphen 90, okay. Iodine hyphen 127. So, that means it is the it is same as the mass number that is given. Okay. Okay. Carbon 13 or carbon 14, okay. Carbon hyphen 14 means carbon element with a mass number 14, okay, because atomic number is always same, right, for a particular element, but mass number will change for different isotopes, okay, that is why. Now, radioactive nuclei, that strontium 90 is a radioactive nuclei of public health significance and its decay follows first order kinetics. Half life is 29 years. How long approximately would a given amount of strontium 90 need to be stored to obtain 98% reduction in quantity? This, if you have done the problems on kinetics, then you can easily solve it, because once the half life is given, you can easily find out the decay constant. Okay. So, half life is 29 years. So, lambda is 0.0239 year, okay. And then for 98% reduction in quantity, you can use this formula, n is equals to atho into n2, this is the n value, and then this formula you can use to find out the T. Okay. So, what is the formula? You have already seen just now, that is the this one, this formula you can use. Okay. This is very simple example. Okay. This is the formula, okay. N by 2, this is n by 2 is equals to n0 e to the power minus lambda into 29, lambda is this one, then 98% reduction in quantity. So, you can find out T for how much. Now, radioactive equilibrium is also very important, very interesting also. So, what you can see here, it is a chain type of reaction, you can see here it is a radium, okay, radium 226, it is the atomic mass number. Okay. Now, here you see it is going to each step one alpha particle is given out. Okay. So, here one alpha particle has gone. So, alpha particle means here atomic mass is written only, atomic number is not written. Okay. Now, upon alpha elimination you see 4 mass is reduced, next another alpha particle, so another 4 mass is reduced, then here another 4 mass is reduced. So, it is a chain type of reaction, radium to radon to polonium to lead, this is the end product. Okay. Now, if you think that the rate, you know, rate is minus dc dt is equals to k into what? K into C, we have seen for first order, here lambda 1 n 1. For this conversion it is lambda 1 n 1, for this conversion the rate is lambda 2 n 2, for this conversion lambda 3 n 3, this is the rate. Okay. Now, when one equilibrium, a radioactive equilibrium is set up, when it is set up, not in all cases, when it is set up, when a radio element with long life is allowed to stand over a long period, long life which has a long life is allowed to stand over a long period, then this type of equilibrium will be set up. Okay. So, in this case you see at that point what will happen, the ratio of the number of atoms of parent and daughter elements becomes constant. Okay. So, ratio of number of atoms of the parent element and daughter element will be constant, okay, at equilibrium. Okay. For the above reaction, say for example, radium disintegrates to radon at a more or less constant rate lambda 1 n 1 over a few months. Radon again passes into polonium at a rate lambda 2 n 2 and then polonium to lead at a rate lambda 3 n 3. So, in a state of radioactive equilibrium, rate of formation of radon is same as the rate of disintegration of radon. Means at equilibrium also we see na, that there is no change, the rate at which radon is formed, at the same rate it is disintegrated. Okay. Then what will happen? The rate of formation of radon is nothing but lambda 1 n 1 and rate of disintegration of radon is nothing but lambda 2 n 2. So, lambda 1 n 1 is same as lambda 2 n 2. Okay. Lambda 1 n 1 is same as equal to lambda 2 n 2. So, n 1 by n 2 is nothing but lambda 2 by n 1 and lambda is related to T half. So, lambda 2 by lambda 1 is equals to nothing but T half 1 by T half 2. So, you can say that number of atoms present is proportional to T half. This means that amount of product at equilibrium is proportional to its half life. Okay. In a general, a radioactive equilibrium exists when a short lived daughter is produced from the decay of a very long lived parent. Long lived parent, short lived daughter, they are daughter elements. This is the end product, but these are daughter, okay, and this is the parent. So, from parent one should be long lived, parent should be long lived and daughter should be short lived, then only this type of equilibrium will be set up. In a general, a radioactive equilibrium exists when a short lived daughter is produced from the decay of very long lived parent. Okay. So, what do you understand from this? In the at equilibrium, if this type of reaction is happening, then at equilibrium, say for example, for particular daughter element, the rate of formation is same as the rate of disintegration, and that time we can write this way, we can find out that n 1 is proportional to T half, okay. N is proportional to T half. It is also, you can conceive also, the amount that will be present here, it is proportional to T half. If T half is more, okay, n 1 is proportional to T half. Okay. So, so n 1 will be more when T half is more. Okay. Very interesting. Now, I thought that maybe if I put some numericals, it will be clear, more clear to you. That is why for each one I have put one numerical. Here you see radioactive equilibrium exists between radium and radon. Same example they have taken as shown in the previous slide. Okay. How many milliliters of radon will be present there under standard conditions of temperature and pressure with 1 gram of radium? Why it is saying that you have to remember that from radium to radon how it is going, 1 alpha particle emission, okay, by 1 alpha particle emission. Okay. So, from there how many milliliters of radon will be present there under standard conditions of temperature and pressure with 1 gram of radium. Given T half for radium is atto years 1590 and T half for radon is 3.82 days. You see here the daughter, it is T half for radium is very long lived parent and very short lived daughter. Okay. Now, just from this you can start N 1 by N 2 is equals to T half by T half 1 by T half 2. Okay. 1 gram of radium is, this is the mass. Okay. So, 1 by 226 gram of gram atom. So, this is the N 1 and then after putting the values in the equation and calculating we get N 2. We need N 2, the value of N 2, then how much gram atom for this radon, and then 1 gram atom occupies this much milliliter at STP. So, the volume of radon after calculating it will come like this. Here alpha particle is not required here, but you have to know because in many numericals you will see that this will be required. How much alpha particle is produced, that will be required, not here, but here, but just simply you can start from here. Everything is given, only N 2 has to be found out and N 2 gram atom you will get just by applying this formula, and then from that gram atom by using this concept you can easily calculate how much milliliter. Okay. Because 22400 milliliter at STP is coming from 1 gram atom. Okay. So, that means this is the relation. So, this much gram atom how much milliliter at STP, what is the volume, that you can easily calculate. Now, unit of radioactivity, this is very important. One interesting thing you can see here, Curie is somebody's name, okay. Rutherford is somebody's name, they are all famous scientists, Becquerel another name, but you see when we use as the unit, you see all are small letters. Okay. So, 1 Curie, the definition, it gives a measure of the rate of disintegration of 1 gram of radium, 1 gram of radium. Okay. How much 1 gram of radium, the disintegration that is producing, that is 1 Curie. Okay. How much it produces? 3.7 into 10 to the power 10 disintegrations per second. Okay. That is nothing but 1 Curie. Millicurie, millicurie means 1000 times less. So, 10 to the power 7, this is same, but this is 10 to the power 7. Then microcurie, so 10 again 1000 times less from the millicurie. Okay. So, this is 4. So, this is according to Curie, millicurie, microcurie. Then Rutherford another unit, this is equivalent to 10 to the power 6 disintegrations per second. This is the Rutherford. Okay. There is Becquerel also, 1 Becquerel, 1 disintegration per second, that is Becquerel. So, 1 Curie is nothing but 3.7 into 10 to the power 10 Becquerel. Okay. There are different units, okay, for the radioactivity. Now, here there is another numericals, that is problem I have given. The half life of radon 222 is 3.82 days, the half life is 3.82 days. What is the weight of 1 Curie of radon 222? 1 Curie of radon is the weight that will produce this much disintegration per second. Okay. Now, lambda is nothing but this one. So, after putting this you can get this value for lambda. Then dn dt is 1 curie, that means this one. So, lambda n means a by 222 into atto, this Avogadro number, okay, where a is the required weight of 222 radon in gram. So, incorporating the value of lambda, and after the calculation we get a is equals to this much gram. So, this is based on the concept of Curie, okay, Curie and the rate constant, that means decay constant, how you can find out all those things. You can do it by yourself. If you understood the previous things, then you can easily do it by yourself, but this is just for practice I have given one. Now, the references, same references. I told you that for this module I have almost all lectures I have kept the same 3 books. You can read from these 3 books if you are interested, and if you want to learn more, obviously you have to go through the books. Okay. These 3 books are very important. Now, in this lecture, radioactive decay process, law of radioactive decay and the half life of the radio element, those things are elaborated. The radioactive equilibrium has been explained and different units of radioactivity are described. Okay. Thank you.